Hello and welcome. In this video, we're going to take a look at the review for AP Physics 1 Simple Harmonic Motion Free Response. Remember to pause and rewind the video as necessary. Let's begin. Problem 1. This graph shows the motion of an object at the end of a spring. So we have a mass spring oscillator, and we're given the mass is 6.8 kilograms. Well, from this, clearly we're given the position time function, velocity time function, and it appears as though we need to come up with the acceleration, net force, kinetic energy, and potential energy versus time functions. Okay, let's do some calculations and figure some things out along the way to make this work easy. The first thing that we need to be able to do is let's identify our basic functions. This clearly is a cosine function, as it is starting from the amplitude at time equals 0. Now the equilibrium position is going to be about right here. So in order to find the equilibrium position, just take the lowest point, the highest point, and then take half of that. Well, the distance from the highest to the lowest point is 0.5 meters. Half of that would be 0.25 meters. So it's pretty clear the distance in between, if we go 0.4 plus 0.25, we get 0.65. So 0.65 would represent the equilibrium position all the way across. Now, the next thing that would be helpful to know, we know that this, well, they're calling it height, so we'll just say y. Y is proportional to cosine of t. This is a cosine function. Your velocity, well, this velocity function is clearly a negative sine function. So velocity is proportional to negative sine. And if you, ladies and gentlemen, remember the pattern associated with simple harmonic motion graphs, we alternate between sine and cosine. So first we have cosine, then we have sine. That means the acceleration function is going to be proportional to a cosine function yet again. But we also need to remember the second part of the pattern. If we're going from cosine to sine, the sign of the function switches. In this case, it switched from positive cosine to negative sine. But when you're going from sine to cosine, the sign stays the same. Since this is negative, this also stays negative. So we're going to be expecting some negative cosine function, something like that. We'll get the details of the function later on when we know what our period is and what our amplitude of that function looks like. Your net force function, since net force equals ma, whatever your acceleration graph looks like, that's what your net force graph is going to look like. The only difference is the net force graph will be taller. It's going to be taller by 6.8 kilograms because you have to go m times a. So it'll be slightly greater amplitude that we have to account for. Kinetic energy is it's equal, obviously, to 1/2 mv squared. But we can say it's proportional to just simply mv squared. So the fact that you're squaring velocities means that you're going to take your velocity graph, and all the portions that are negative will essentially become positive, like that, and then multiplied by the mass. So we should expect something that resembles this. Again, we'll get the details of that graph as we find the period and the amplitude of it. And your potential energy function of a spring is equal to 1/2 kx squared. So in other words, potential energy relates to the position function, just like kinetic energy relates to the velocity function. So we should expect the negative parts of the position function to essentially be up like this, and we should see a function that looks a lot like that. Once we find the kinetic energy function, the amplitude here becomes the same amplitude here, but at different locations at different times. Okay, so let's put all this work together. First, let's find the period. Well, how do we find the period? The period is when the graph, the function, repeats one time. So there would be your period. There's the repetition right there. You can see it repeats every 2 seconds. The period is 2 seconds. Now, what's the frequency of motion? Well, frequency is the inverse of the period. So 1 over 2 seconds is 0.5 hertz. Part 3, the maximum acceleration experienced by the object. Well, A max can be found by taking the amplitude times omega squared. So we need to find this thing called omega. How do we do that? Let's go back to period. Period is equal to 2 pi over omega. Well, that means omega is equal to 2 pi over the period. So 2 pi over 2 seconds means that omega is pi radians per second, or approximately 3.14 radians per second. So A max is equal to the amplitude. Now, what's the amplitude of the function? Well, remember, guys and ladies, the amplitude of the function, let me get rid of these, is the height from equilibrium, which is 0.25 meters. So the calculation is going to be 0.25 times pi squared. And we roughly get about 2.5, about 2.5 meters per second squared. That helps us create the acceleration function because we know how tall it's supposed to be. It's going to be 2.5 meters per second on top and bottom of equilibrium. And it's going to repeat every 2 seconds, just like the position and velocity graphs do. So let's scale this thing. I could go 1, 2, 3 in that direction, -1, -2, -3 in that direction. The amplitude is going to be, it's going to go as high as that point, as low as that point. I like making horizontal asymptotes to guide the height and depth of the graph. I'm starting the graph here at the low amplitude because that's what a negative cosine graph, remember the negative cosine graph looks like that. So then what I'm going to do is I'm going to repeat that dot every 2 seconds. It'll come back down to that point every 2 seconds. So 0, 2, 4, and at the seconds in between, it'll be at the other amplitude on the top. Just like that. And then we just fill in the nice smooth curve in between all that. And we have our acceleration as a function of time. Okay, let's find the net force so that we can graph that particular one. Net force is equal to MA. So net force is going to be equal to 6.8 kilograms times essentially A max. So maximum net force corresponds with maximum acceleration, which was, if you remember, 2.5 meters per second squared. And we roughly get about 17 newtons. Let's calculate the maximum kinetic energy and the spring constant so we can figure this out. So maximum kinetic energy, K max, is 1/2 mv max squared. So 1/2 times 6.8 times V max. We didn't calculate V max, but you can get it from the graph. This is V equals 0. This is V max right here. That's 0.6, 0.7, 0.8. That's 0.8 meters per second. And that comes out to roughly about 2¼ joules. Okay, now something important to note. This is the maximum kinetic energy at equilibrium. Well, something to note, the maximum potential energy is also 2.25 joules because, again, law of conservation of energy, right? At the amplitude position. So it's the same maximum energy, but at different locations. And finally, the spring constant. Well, the spring constant can be found by relating to the square root of k over the mass. And if you don't remember this, just simply go to your 2 pi equal to the square root of m over k equation and solve it for k. You can do it that way. I prefer to do this way. It's a lot less work. Square both sides and solve for m. No, solve for k rather. Multiply both sides by m. So we have m omega squared, 6.8 times pi squared, and k is approximately 67 newtons per meter. Now, there's yet a third way you could do this too. Say you didn't remember this, you could solve for k using that method, or you could also go kx equals ma, because kx is your spring force, but that's also your net force. And so k would be ma over x, which is 6.8, over the maximum acceleration of 2.5, divided by the maximum displacement of 0.25. This is 10 times 6.8 is about 68 newtons per meter. So you can see we're getting roughly about the same thing using two different methods. Okay, let's complete those graphs. The maximum net force, F max, was 17 newtons. So, I don't know, I'm thinking, let's make this 10, let's make this 20, and every box is 2 going up. That's a pretty easy way to scale this. I would put negative 17 about right here. So remember, a net force graph is supposed to look like an acceleration graph, meaning if this is negative cosine, this will be negative cosine too. So you expect it to look like this also. But I'm going to put my asymptote in there on both sides. That's 17 newtons all the way across, and negative 17 newtons all the way across. That way I just kind of know exactly where to cap off the highest and lowest point of my function. I'm starting my graph at negative 17. Every 2 seconds I get back to negative 17, because again it's a negative cosine function. All the other times in between, I'm at the positive amplitude, and my graph is just simply a taller version of the acceleration time graph. Still repeats every 2 seconds. The kinetic energy graphs will always look like the velocity graphs. Just take the negative portion of the graphs and flip them up. Okay, so in other words, we will expect the graph to look like this. Okay, but we need to know what the maximum value is. We know you've got 0 here. Here's the bottom. That's the lowest possible point of kinetic energy. You can't get anything lower than 0. But the maximum kinetic energy is about 2.5, or not 2.5, 2¼ joules. So I can go 1, 2, 3 going up, -1, -2, -3 going down, something like that. 2 1/4 would be right here. Halfway between 2 and 2 1/2. Really helpful to put your horizontal asymptotes all the way across. So it'll help guide the graph. You know you're starting at 0. You know you're going to essentially come back to 0 every single second. Just like that. And that means the rest of the graph goes up as a maximum at half a second, 1 1/2, 2 1/2, 3 1/2, 4 1/2 seconds. Something like that. Now your potential energy graph will be exactly the same thing. It will just be shifted over like this, where it starts like a cosine graph. It starts at the top. Okay, it'll have the same exact maximum values, same scale, everything is the same. The difference is where the maximum minimum values are. So I'm just going to copy this right down, make it really easy for me. I'm going to erase the graph. I'm going to erase those dots. This time, I remember that I have my potential energy graph starts at 0, and every second it's going to come back up to 2 1/4 joules, just like that. The minimum will always be 0. You're not going to get lower than that. And it'll simply alternate between those points. Very easy to come up with. Part B. Complete all the graphs above. Well, we did that. Label all the maximum minimum on the graph. We did that. So again, pause and rewind as necessary to get these calculations and graphs completed correctly. Problem 2. A student is testing to see if the mass oscillating at the end of a rubber band exhibits simple harmonic motion. The student uses a force sensor, a motion sensor, and a force sensor to find the rubber band's force and masses. Height is a function of time. The 3 trials are shown below. So obviously in this question, to be able to answer it, you need to know essentially what makes something simple harmonic motion and what doesn't. Simply going back and forth, like these graphs are all showing, may or may not cut it. So let's review. Number 1, all simple harmonic functions will be sinusoidal. That's number 1. Well, those are sinusoidal, so it seems to fit. 2, force, net force, and thus acceleration are directly proportional to the opposite of displacement. So in other words, net force and acceleration would be linearly related to how far it's away from the equilibrium position, but opposite. 3, period does not depend on the amplitude. Okay, meaning if you pull it back farther and stretch it, it's not necessarily going to go and oscillate for longer. The period is not related to how far it's pulled back from equilibrium. So, a couple of things I notice. The period of this function here is less than 2 seconds. Period of this function is 2 seconds. The period of this function is 2.5 seconds. So clearly we have a situation here where the amplitudes are different and they're giving you different periods. This is showing you that the period is dependent on the amplitude. So this is probably my first indicator that the motion is not simple harmonic motion. We can also see that here, the height and the force. So when we have a little force applied and versus a large force applied. So force versus height on this graph right here, you can see it's getting smaller and smaller. So there seems to be some relationship there it shouldn't have to be simple harmonic motion. So let's take a look. The student also has access to a physics textbook with the following excerpts. So here's another review of what it means to be simple harmonic motion. Not all oscillations, that means periodic motions, qualify as simple harmonic motion. Simple harmonic motion is a special class of oscillatory motions. To qualify as simple harmonic motion, an oscillation must meet the following requirements. Again, it must be sinusoidal. That means a sine or a cosine graph. The net force must be acting linearly with the object's position, and the acceleration must be acting linearly with the object's position. The net force must be opposite to displacement. In other words, displacement goes up, net force goes down, and so forth. The period must be independent of the amplitude. In a clear, coherent, paragraph length response, conclude whether or not the motion is simple harmonic motion, state evidence to support your reasoning. Well, here's what I noticed. The object is not undergoing simple harmonic motion. The graph is sinusoidal. However, the force is not linear with position. Just look at the graphs above. That is not a linear function. That's a linear function. That's a linear function. That's a linear function. That's a linear function. The period of, that's a typo, of oscillation should not depend on the amplitude. However, again, in this one it seems to. The period changes clearly as the amplitude has changed. Part B. Now consider a ball that is perfectly elastic that drops from rest at some height. The ball bounces such that on each bounce the ball rises up to the same height from which it was dropped. Explain whether the simple harmonic motion. You may draw graphs or diagrams to aid in your response as appropriate. Again, not simple harmonic motion. To be in simple harmonic motion, the force needs to be proportional to displacement. Well, that's not true. As a ball falls to the ground, gravity is constant, no matter where it's on its way down. Problem 3. A thin, flexible metal plate is attached at one end to a platform as shown above. Can be used to measure mass. This is called, by the way, an inertial balance. This is something in terms of what an astronaut might use aboard the International Space Station to weigh a particular object and figure out mass, since obviously a spring scale or a balance to put a mass on, which depends on gravity, would not work very well. So it says when the free end of the plate is pulled on, typo, pulled down. So if it's pulled down like this, it's going to oscillate up and down at the end. It vibrates in simple harmonic motion with a period that depends on the mass attached to the plate. To calibrate the force constant, and thus figure out what the force constant is, objects of known masses are attached to the plate. The plate is then vibrated. So this is very, very similar to a mass oscillating at the end of a spring. Thus, we're going to use the exact same relationship. The equation we would use is 2 pi equals, or 2 pi times the square root of m over k. Let's begin by squaring both sides. We get t squared equals 4 pi squared m over k. Then I'm going to separate variables from constants. Well, according to this, period and period squared are my variables. Mass is clearly a variable. So period squared and mass are my variables. I highlighted them in blue with a V. 4 is obviously a constant. Pi is obviously a constant, so pi squared would be a constant. And k is the spring constant I'm looking for, so that's also a constant. We're going to essentially divide both sides by the mass, like this. And we're going to write it as our fraction, rise over run, to be able to get the slope. The rise is your vertical axis. The run is your horizontal axis. This means you're going to be plotting t squared versus the mass. Like this, t squared on the y-axis, mass on the x-axis. But that'll be equal to 4 pi squared over k, which is thus the value of your slope. So to find your slope, you simply switch those two. K would be equal to 4 pi squared divided by our slope. We'll come back to this one shortly. First, let's figure out the rest of this table. If the average time for 10 vibrations is in this column here, all we need to do to get the period, which is the time for one oscillation, is simply move the decimal one place to the left. In other words, divided by 10. And we get 8.86, or is a period of 0.886, 1.06, 1.35, 1.47, and 1.77. This is supposed to be t squared and seconds squared. So 0.886 squared is 0.785. 1.06 squared is 1.12. 1.35 squared is 1.82. 1.47 squared is 2.16. 1.77 squared is 3.13. Again, pause and rewind as you need to. What you need to now do is plot t squared on the y-axis versus mass on the x-axis. The scale's already been created for you, so you simply need to plot. Should end up looking something like this, with our first plot point around here, second plot point, third, fourth, and fifth, with a best fit line that gets drawn in between them like this. Please pause the video at this point to go ahead and complete your graph. Okay, now that the graph is completed, we're going to find two what are called convenient points. That means where the graph is intersecting the graph paper, like that, to essentially find the value of our slope. We're going to go rise over run, and we're going to get our slope from that. Our slope is roughly about 0.6 over 0.1, which is the same as 6 over 1, which is 6. So we'll use that slope of 6 soon enough. Part C, an object whose mass is not known is vibrated on the plate, and an average time for 10 vibrations is known to be 16.1 seconds. So from your graph, determine the mass of the object. Well, here we go. First, T10 is given to us, 16.1. That means the period, move the decimal over 1 divided by 10, is 1.61 seconds. You're going to square your period to get t squared, 2.6 seconds squared. Then what we do, ladies and gentlemen, is we go to 2.6 seconds on 2.6 seconds squared on the graph, which is exactly right here. You follow it over all the way to the graph, which is right here. Then you can see it meets the graph right at that spot. Then you simply go down and you are interpolating what the data is. That would be approximately 0.45 kilograms. Determine the force constant of the metal plate. Well, again, you're going to find the slope. We found a slope of 6 earlier. Recall, slope equals 4 pi squared over k. Switch them, so k is equal to 4 pi squared over slope, which is 4 pi squared over 6, which is approximately 6.6 newtons per meter. Again, please make sure to rewind the video and pause as necessary, and thank you.